Hello, everyone. Thanks for joining us today. My name is Cordell Cahoon, a junior in mechanical engineering here at UC Davis.
Hi, my name is Balram Kandoria. I'm a double major in aerospace and mechanical engineering, and it's currently my fourth year at UC Davis.
Hi, my name is Ashir Bhalla-Levine, and I'm a first-year material science and engineering major.
And today we'll be presenting our poster on the development of a novel propulsive lunar mobility and gravity emulating platform. So to start with some of the background, it's that mobility is absolutely critical in any sort of robust surface operation. And this is particularly true for NASA's return to the moon, as any settlement which hopes to ensure sustainability would need access to large stores of water and other resources. And some of the most promising areas to gather these resources are the poles, as they have permanently shadowed regions, which are craters that do not receive any sunlight due to their relative angle to the sun. And these have been shown to contain deposits of ice and some other hydrogen-based substances. So in order to mine those deposits, reconnaissance operations, likely robotic ones, are going to be required to locate those deposits. These PSRs feature a pretty wide array of difficult mobility challenges, like unknown surface material characteristics, like how soft the material is, and rough terrain, and then steep slopes near the crater rims. So our solution, our offered solution to this, is a propulsive hopper system that allows avoidance of obstacles such as large boulders or otherwise impassable slopes and canyons. So moving into the objectives of the research and the concept of operations for the hopper. The research was conducted to design an Earth-based testbed of this lunar hopper system. We called it the Lunar Emulated Hopping Platform, LaHop, as part of NASA's Big Idea 2020 Challenge. It was sought to generate early best practices and research into the viability of such a device in order to further NASA's strategic goal of lunar exploration. And to fulfill the lunar concept of operations, where the platform must be able to enter and return from a PSR, the mission requirements prioritized included that the platform shall be capable of moving itself in a small payload, be capable of avoiding difficult terrain, and be capable of communicating data to a nearby relay. The mobility subsystem aspects of this platform are the ones focused on in this presentation. So moving to the propulsion system, the hopper's propulsion system consists of 3 70-Newton resistojet thrusters, which are ejecting heated nitrogen gas at a mass flow rate of around 68 grams per second per nozzle. Each of those resistojets is comprised of a titanium thrust chamber and nozzle in order to deal with the temperatures we'd like to get it to. And they have an embedded commercial off-the-shelf cartridge heater along with an insulating layer. How it kind of works is that the propellant inlet guides the cold stored gas into the thrust chamber, where it then meets the cartridge heater, and a positive delta T is applied to the propellant. So the converging diverging nozzle, it has a throat diameter of about 5.6 millimeters and an area expansion ratio of around 3 for ideal expansion at sea level. This is a CAD model of roughly how it would look, along with a couple diagrams of how that system would be built. And now we'll move on to the Mach gravity system.
Thank you, Cordell. The Mach gravity system is essential for Earth-based testing of this platform. And the system consists of a power supply and 3 ducted fans, which would be attached equidistant around the hopper. Through the thrust of all 3 fans, the Mach gravity system would activate prior to the propulsion system and offset 5/6 the force of Earth's gravity on the platform, as well as the force of gravity on the apparatus itself. When the system is off axis during a propulsive maneuver, the fans would throttle thrust to ensure a constant upward force is being experienced. And that upward force increase would also cause the system to drift a little further horizontally, which can be accounted for during flight tests. And to the right of the text there, you can see a system schematic for the Mach gravity system, and below in the center of the poster, you'll see kind of a lunar concept of operations, except with a little addition for the propulsion system and Mach gravity system, how they work together, along with some equations that model the Mach gravity system itself. Below that, we've got the attitude determination and control system. The attitude determination system is necessary for LHOP to assess its attitude relative to the surface. It's comprised of 3 inertial measurement units with drift correction from a global navigation satellite system. The attitude control system is used to aim the hopper and consists of 3 motors and flywheels oriented in the x-axis, y-axis, and z-axis relative to the vehicle's reference frame. A 4th redundant wheel is commonly placed offset to each of the axes and is omitted in the diagram for simplicity, but is used in case any one of the wheels fails during maneuvering of the platform itself. Now we're going to move on to trajectory and fuel optimization.
Hi, thank you, Ashir. The trajectory and fuel optimization is an important parameter for our LHOP to determine how far our LHOP can travel. In order to find the most fuel optimal hopper trajectories and how far the system can hop in a lunar environment, we used the modeling language CYXPY, which was used in conjunction with MOSEK, a large-scale optimization software. Formalization of the problem follows the basis of the G-fold algorithm developed at NASA JPL and SpaceX, which has enabled fuel optimal precision landings of the Falcon 9 rocket. 2 different hop distances were modeled to reflect realistic conditions, 100 m representing the distance from CLPS lander to the PSR, and a 1,000 meter representation to the distance from the PSR to the rim of the CLPS lander. The first graph on your left represents the 100-meter case with a fuel consumption of 0.88 kilograms, with a total flight time of 2.65 seconds. The graph on the right shows the results for the 1,000-meter case, which requires our LHOP to have a 2.65 kilogram payload and a time of flight of 40.5 seconds. With that, we'll move on to the conclusion.
So the 2 big takeaways from this research were that the first one being long hops are more efficient than short ones. So with a 1,000% increase in distance between the 2 scenarios modeled, fuel consumption only increased by 201%. So this result may serve to guide the flight planning of future lunar hoppers that are trying to achieve optimum distance to fuel consumed. And the second point is that hopper systems are likely a viable means of exploration. So with fuel consumption in the single digits of kilograms for potentially thousands of meters of distance traveled, propulsive hopping represents enormous potential for lunar exploration beyond traditional rovers. And now we'll go into the future development of lunar hoppers.
Thank you, Cordell. While NASA's Big Idea Challenge 2020 has concluded, the process of designing LHOP led to the identification of several systems that need to be addressed for a successful lunar hopper. Thermal management of fuel and rocket nozzles, our N2 fuel and other fuel candidates freeze at PSR ambient temperatures, and frost accumulation in the nozzles may cause ice chokes, reducing our mass flow. Resistojet efficiencies need to be recorded and tested. The relevant delta T needs to be measured, and the effects on mass flow and therefore thrust performance need to be taken into account before implementing the thrusters, the resistor-jets on the thrusters. Collision avoidance needs to be studied to avoid tipping of the LHOP on landing and for active in-flight avoidance of large boulders and other debris. With that, we'll move to the acknowledgements.
So now we'd like to offer our utmost gratitude to Professor Stephen K. Robinson, Dominic Phillips, Abhinav Kamath, and the rest of the LaHop team for all their hard work throughout fall quarter and a little bit of winter quarter.
Thank you for checking out our research, and feel free to leave any comments on the video using the UC Davis hosting tool, or any questions you may have about the project. And have a nice day.